Hi chemists! In this video we are going to focus on the relationships between units of pressure and temperature and kinetic energy. After this video you should be able to convert between units of pressure and explain what mathematically would occur if the average kinetic energy and temperature are changing. Gas pressure, as you may recall, is the simultaneous collisions of gas particles, and we talked about popcorn popping with gas pressure. And pressure is measured in different units: atmospheres, kilopascals, and millimeters of mercury. All pressure conversions can be done in a single dimensional analysis conversion. So here's an example. So it says the pressure inside a balloon is 4.17 atm. How many kilopascals is this? Just like we always do, we'll start with our known and our unknown, and we'll take our known, put our multiplication sign in. And you want to ask yourself the question, what conversion factor are you using? We know that 1 atm equals 760 millimeters of mercury, which also equals 101.3 kilopascals, but we can't use all three of these. So we are going to focus on the fact that 1 atm equals 101.3 kPa because our known is in atm and our unknown is in kPa. So we will take our 1 atm, put that on bottom, and then 101.3 kPa is going to go on top. We're then going to have to do our multiplication, and the number of sig figs is going to match the number in the known. So it should be 422 kilopascals as our answer. If the calculation were different and it asked for how many millimeters of mercury this would be equal to, fortunately the setup is the same. The only difference is on the top here. You would just replace the 101.3 kPa with 760 millimeters of mercury. In a sample of matter, it's important to note that not all particles are moving with the same speed. And so temperature, as we mentioned, is a measure of the amount of kinetic energy that a sample of matter has. And it is true that most particles are moving with the average kinetic energy. However, some are moving slower and some are moving faster. So that's why not all particles in a sample have the same amount of kinetic energy. And so if you look at this sample on the right-hand side here, you can very clearly see that there are some particles that are moving much slower and some particles that are moving very fast. And you can also see that in this graph right here, notice the y is number of molecules. You can see that in the center of this curve, this is really your average. So for example, in a gas, you can see that most particles are moving with an average speed. However, some on the right-hand side are moving faster than average and some are moving slower than average. As you increase temperature, the speed of the molecules is going to increase. So notice that this red line indicates a hot gas, and you're going to see the speed of those particles increase, and so the average speed is going to be greater as a result of the temperature being greater. Average kinetic energy is directly proportional to the Kelvin temperature. And what that means is that the factor by which your kinetic energy would go up, that would be the factor by which your temperature would go up, as long as it's in Kelvin. So it's important to note how to figure out what the temperature would be in Kelvin. And so fortunately, it's a really easy calculation. All you have to do is take the degree Celsius temperature and add 273 to it. Kelvin, it's important to note Kelvin is never a negative number, so you should never get a negative answer when you're doing this. So for example, we know room temp is equal to 25 degrees Celsius approximately. What is this in Kelvin? You would take the 25 degrees Celsius and add 273 and you would get 298 Kelvin. Notice it's written as 298 K. It's not written as 298 degrees K. There's no degree sign included in Kelvin. As temperature decreases, we know that the particles will continue to move slower and slower. So we may say that particles would theoretically stop at this temperature called absolute zero. And absolute zero is 0 Kelvin, but we know that according to kinetic molecular theory, all particles of matter are in constant motion. At this point, absolute zero may or may not have been reached. I know when I first made this PowerPoint, we came very, 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 very close, but I'm not sure if we've reached it yet, but you might want to maybe do some research if you're interested. Standard temperature and pressure, remember, is abbreviated STP. Standard temperature and pressure will equal 0 degrees Celsius or 273 Kelvin. So now we're going to talk about calculating the factor by which kinetic energy changes given a temperature. So it says since kinetic energy is directly proportional to the Kelvin temperature, the factor by which kinetic energy increases or decreases can be easily calculated. So for example, if your temperature goes from 200 Kelvin to 400 Kelvin, then the average kinetic energy will double. So if you do 400 over 200, you'll get it by a factor of 2. You want to, when you're doing this, always put the final temperature over the initial temperature. That'll make it easier for you to tell what it should be. Here's another example. If temperature goes from 100 to 300, then the average kinetic energy will triple. And so 300 over 100 is how we show it mathematically, so that'll be 3. If temperature goes in the opposite direction from 300 to 100, then the average kinetic energy will be a third. So you do 100 over 300, and that will be 1/3. Here's another one. If temperature goes from negative 73 degrees Celsius to 127 degrees Celsius, then the average kinetic energy will, be careful here, kinetic energy is proportional to the Kelvin temperature, not degrees Celsius. So that means for you is you need to convert both of these temperatures into Kelvin. And you can see this is a similar example from before. It'll double, and again 400 over 200 will give you 2. So I hope this video was helpful in understanding how to convert in between units of pressure and what the relationship is between kinetic energy and the Kelvin temperature. Thank you so much for watching.